All right, now we're going to talk about waves, mechanical waves and electromagnetic waves. What do they have in common and how are they different? Let's get started. All right, so as you can see here, the information in this presentation comes from three different sections, 17.1, 17.2, and 18.1. And there's a lot of information in those two chapters. What we're going to do is try to lay down sort of a base of understanding of what waves are, the components of waves, and how they're related. At the end of this, we're going to try to get back to the idea of an expanding universe and talk about how the apparent change in wavelength is used as evidence to prove that the universe is in fact expanding. All right, so waves transport energy and not matter. Now in this picture here you can see Kelly Slater being moved on his surfboard by a very large wave, but that wave is actually crashing, perhaps on a reef or on a beach, and so it's sort of toppling over. And in that case, the wave can then therefore move matter. We'll return to this in general, but for this presentation, when we think about waves, we want to think about sort of the movement of energy as opposed to matter. All right, let's start with mechanical waves. A mechanical wave requires a medium to actually move. And so as you can see here, solids, liquids, and gases can all act as mediums. And a mechanical wave is caused when an energy source causes a vibration or a disturbance to travel through that medium. Okay, so there are three types of mechanical waves. In a transverse wave, the medium vibrates perpendicular to the direction of energy flow. In a longitudinal wave, the medium vibrates in the same direction as the energy flow. And a surface wave travels along the surface that is separating two medium, for example, water and air. And I'll show you diagrams of those now. Okay, here's a diagram of a transverse wave. As you can see, the spring is being moved vertically up and down, and the energy flow is horizontally. So it's moving left to right or right to left across your screen. And this may actually help you to remember that. In a longitudinal wave, the medium vibrates parallel to the wave's motion. So in this particular diagram, the movement of energy and the movement of the spring itself is in fact horizontal. So we have compression and rarefaction as the spring is compressed and then opens and compressed and then opens time and time again. Surface waves, the movement of surface waves is sort of a combination of longitudinal and transverse motion. So there is a vertical and a horizontal motion, and what results from this is a sort of circular motion, as can be seen in this diagram here with the bobber. So if you're out to sea on a boat and you happen to see something bobbing along, it's really not being moved by the wave. There might be other factors moving it, such as current or wind speed, but the wave itself would not actually move that bobber. If you're near the shore, as I discussed before, as the wave crashes, it can carry the medium with them. The water itself is actually going to move forward, and so that would carry the bobber, or you on your surfboard, towards the shore. All right, here we can see sort of the anatomy of the wave. We have the crest, which is the high point of the wave. We have the trough, which is the low point of the wave. And then we have that equilibrium position, sort of like the neutral position in the center of that wave. And if we talk about amplitude, we're talking about the maximum distance the wave moves away from this equilibrium position. And that's measured in meters. More energy, it will equal a higher amplitude. Okay, so the wavelength is the length of a single complete wave. We're going to use the Greek symbol lambda for that, and that will be measured in meters. The frequency is the number of cycles per second. Keep in mind that a wave is a periodic motion, and so it's going to repeat itself at a consistent speed. And finally, the velocity, or the speed of the wave, is the velocity of the wave, and that's measured in meters per second. Frequency, I should say, is measured in hertz, which is cycles per second. Okay, here's a diagram to show you wavelength. In this case, we're using crest to crest. You could use trough to trough. You could use any two corresponding points on that wave to figure out the wavelength. And again, that's measured in meters. Okay, as we said, waves repeat at a regular time interval, and the frequency is the number of complete cycles in a given time. And we measure that in cycles per second, which is known as hertz. So what determines the frequency of a wave? Well, it is equal to the frequency of the vibrating source that is producing that wave. Okay, I really like this visual below to show the relationship between frequency and wavelength. And as you can see, that frequency and wavelength are inversely proportional. So increasing the frequency of a wave would decrease its wavelength. And the top wave has a higher frequency, And to calculate the speed of the wave, you can multiply the wavelength by the frequency. In the next section, we'll be talking about electromagnetic waves, and we'll see that the speed of light remains constant. Here's a diagram of an electromagnetic wave, and in many ways it's very similar to a mechanical wave, but as you can see, EM waves do not require a medium. Therefore, they can operate in a vacuum, they can operate in space, they can move through space. So light from distant galaxies or from our sun can make its way to observers here on Earth. How does that happen? Well, there's a magnetic field and corresponding electric field that in fact regenerate themselves as this wave moves forward. For right now, we don't really need to concern ourselves with that. You probably noticed that it is a transverse wave in that the vibration of the wave is perpendicular to the direction that the energy is in fact flowing. In other words, an electromagnetic wave is a transverse wave that consists of changing electric fields and changing magnetic fields, and they're created when an electric charge vibrates or accelerates. As indicated earlier, the speed of light is in fact constant, and the speed of light in a vacuum, or we're going to use C to indicate that, is 3.00 times 10 to the 8th meters per second. And that's constant regardless of the observer's motion. So whether you're moving to it or away from it, it doesn't matter. The speed of light remains constant. While electromagnetic waves all move at the same speed, of course, they do vary in their wavelength and frequency. All right, let's take another look at that EM spectrum. And on the very right, we see radio waves, and they are essentially harmless to us. They're all around us. They're passing through our houses and school and through us all day long, and we don't notice them. Notice the wavelength. They're very long wavelengths in comparison to the other waves on this spectrum. 10 to the negative 1 up to 10 to the third, you see, actually named on this spectrum here. Another lower energy, longer wavelength wave that you're familiar with probably would be microwaves. Perhaps you use those in your home to cook your breakfast or whatever. Now, moving left, you see that the energy increases and the wavelength, in fact, decreases. And so if you go to the beach in the summertime, you probably know to put on sunscreen to protect you from the sun's harmful UV rays, protect against sunburn, of course. And if you go to the doctor, the dentist, and have had an x-ray done, you know that they're going to put that lead vest on your chest to protect your organs from the even more harmful x-rays. And way on the left-hand side, you have these high energy, high frequency, very short wavelength gamma rays, which are in fact very dangerous. Now, all of the visible light that you and I can see occurs in that sort of 10 to the negative 6th region, that little sliver there that's left white on the spectrum. And within the visible light spectrum, you can see that differences in wavelength and frequency are perceived by our eyes as differences in color. Around the 400 nanometer region, you have purple and blues and so forth. And around the 750 nanometer region, you have the reds. Just keep in mind that regardless of the wavelength and frequency, all of these EM waves are moving at a constant speed. Now that we've made some observations about light and waves, and we've actually sort of built a foundation of how waves work, we're going to be using this equation below to calculate the frequency and wavelength of electromagnetic waves. Okay, I hope that was helpful. Again, we'll be taking these ideas and sort of relating them back to the idea of an expanding universe. If you have any other questions, please feel free to ask them in class or just send me an email. Take care.